Welcome to Ask and Learn.
3 moles of an ideal monatomic gas expands at a constant pressure of 2.5 atmospheres. The volume of the gas changes from 3.2 times 10 to the minus 2 meter cubed to 4.5 times 10 to the minus 2 meter cubed. Calculate the initial and final temperature of the gas, the amount of work the gas does in expanding, the amount of heat added to the gas, and the change in internal energy of the gas. So let's start by writing down what's given to us. So we have that the pressure is 2.5 atmospheres. We have that the final volume is 4.5 times 10 to the minus 2 meter cubed, and the initial volume is 3.2 times 10 to the minus 2 meter cubed. And next we want to get for A, we want to get the initial and final temperatures. And I'm just going to write in a different color because this is sort of a lot of writing to do. So I want to make sure it's clear. So A, not equals. To get the initial and final temperature, we want to use the ideal gas law. So that's PV equals nRT. And then if you rearrange it, then you can get T equals PV over nR. And we can basically just plug in, we have all of the quantities that you need to calculate the temperature. They're all in SI except for, the volumes are in SI, but the pressure isn't in SI. So I'm just going to come up here and kind of convert it. So 2.5 atmospheres, and then we want to multiply it by 1.03 times 10 to the 5 pascals per atmosphere. And with that, we obtain 2.58 times 10 to the 5 pascals. Okay, great. So now that that's an SI, we can go ahead and just plug that in. So then it's 2.58 times 10 to the 5 pascals times, so if we're going to do the initial one, I'm just going to erase this and not write equals, but I'm just going to say that, T initial equals that times the V initial, 3.2 times 10 to the minus 2. And you just want to divide that by the number of moles. Oh, I don't think I recorded that up here. Let me go ahead and do that. So there's 3 moles. N equal 3 moles. Okay. So 3 mole. And R is 8.31. Let's see, what are the units of that? I think it's joules per Kelvin mole. Yeah, that works out. Okay. So if you plug that into a calculator, you'll get an answer in kelvins. So let me just quickly do that math out. And so 3.2. So you got 331 Kelvin for that. So to get the T final, oops. To get T final, you just want to plug everything into your calculator except for the same things that you plugged in before into your calculator, except instead of 3.2, you want to use 4.5 because that's the volume finally. So you want to send that to 4.5 times 10 to the minus 2 meters squared. And then if you plug that in your calculator, then you get that T final equals 0.032, 0.05. You got 465 Kelvin. And I'll go ahead and box these answers. So it's clear what the right answer is. Oops. Kind of running out of room. Okay. So for B, what does the question ask? For B, it asks for the amount of work that the gas does in expanding. The amount of work that the gas does, the amount of work done by the gas, it's always the area under the PV curve. And since P is constant, it's just going to be P delta V. And then that's equal to 4.5 times 10 to the, I'm going to do pressure first. So that's equal to the pressure, which was 2.58 times 10 to the 5 pascals times 4.5 times 10 to the minus 2 minus 3.2 times 10 to the minus 2. Both of those are meters cubed. And if you plug that into a calculator, you get 6,600 joules. Great. So then next, you want to get, C asks for the amount of heat added to the gas. And I'm actually going to do that at the end because I think part D is easier to calculate, which is the change in internal energy of the gas. So, oh yeah, I'm also going to circle this before I move on. So there's work by. Okay. And then for D, so to get the change in internal energy, you want to use delta U equals 3/2 NR delta T, which is true if the number stays the same. Otherwise, more generically, U is equal to 3/2 nRT. And so we can just go ahead and plug in our delta T that we calculated in A. And I'll actually write that out. So N is 3 moles. R is 8.31 joules per Kelvin mole, and delta T is just 465 minus 331. It's like slightly sloppy. I'm just gonna correct that 331 just to make sure it's clear what it reads. Okay, there we go. And back to part D, if you plug all of that into a calculator, then you get that delta U is 9,900 joules. Okay, now you can go back to part C. For C, you want to use the equation that Q equals the work by the gas plus delta U. And so we can just add the answers from B and C. So 6,600 joules plus 9,900 joules. And you can get from that 99 plus 66 is 165. Zero, zero, so 16,500 joules. And then kind of hard to box that from my screen, but there's a box.